Hi, in this video I'm going to be solving a design problem and finding the lightest A992 steel W shape that meets the requirements for this roof beam with the given factored distributed loads. The first step would be to solve for support reactions, and if we consider this point A and this point B, we can sum moments and find out that AY is equal to 71.25 kips. And by is equal to 138.75 kips. From that we can draw shear diagrams. And in terms of kips, we start on the left side at the value of the support reaction, 71.25. We have 3 unbraced segments, and at the end we end up at negative 138.75 kips. And we find out as we use the slope of shear as the value of loading that at 14.25 feet from the left end we end up crossing 0. And it's about here, and our shear diagram will look something like this. So the slope abruptly increases in segment C, where the value of loading increases. So we're going to next go and do the moment diagram, but before we do, we need to find C sub B. So thinking ahead to doing any kind of unbraced beam design, we're going to need C sub B, and that means we're going to need the values of moment at the quarter points. So in order to get the values of moment at quarter points, we're going to first solve for the value of shear at those quarter points. So while we're here on the shear diagram, I'm going to label the quarter points of each shear segment, which you can easily get by looking at the value of loading in the loading diagram above. So the quarter points along segment A are spaced at 2 feet apart. Moving on to segment B, these quarter points are spaced at about 2.5 feet apart. And so the value of shear at these quarter points are going to be 18.75, 6.25, and negative 6.25. And then at the juncture between segment B and C, we have a shear of negative 18.75. Along segment C, the quarter points are 1.5 feet apart, and the values of shear negative 48.75, negative 78.75, and negative 108.75. Okay, knowing that the value of moment at, say for example, the first quarter point is equal to the value at the left end of moment plus the area under the shear curve, we can draw the moment diagram. So we know moment starts and ends at 0, being a simply supported beam. We know that it's going to have a maximum where shear is equal to 0. And then it's going to more steeply drop off once we have the greater magnitude of loading. Okay, so we can break this up into segments. This would be segment A, segment B, and segment C. And again, we're interested in the quarter points. So knowing that the area under shear is the change in moment between 2 points, we can get all these values, 132.5, 245, 337.5, and 410 at the juncture between segments A and B. Quarter points of segment B are going to be 503.8, excuse me, jumped the gun, 472.5, 503.8, and again 503.8. So this isn't drawn exactly perfectly. What happens here is between two of these points on the moment diagram we have a peak moment. And that value of peak moment is 507.7. And then it's symmetrical on either side for a little while until the value of loading changes. So the value of moment is 472.5 at the juncture between segments B and C. And then at the quarter points of C, we have 421.9, 326.3, and 185.7. Make sure you pause the video at this time and ensure that you are able to do this without error. Getting the moment diagram is a very important thing. And one other thing we want to label that helped us get to this point and get to these moment values is the fact that at 14.25 feet from the left end, shear crosses zero. Alright, the whole point of us finding the quarter point values of moment was to be able to solve for C sub B. So C sub B for segment A is going to be 12.5 M max over 2.5 M max plus 3 MA plus 4 MB plus 3 MC. So plugging in our values for segment A, we have 12.5 times 410, and I'll leave off units just to make things a little bit less cluttered. 2.5 times 410 plus 3 times 132.5 plus 4 times 245 plus 3 times 3, 37.5, and we get CB is equal to 1.50 for segment A. You can use that same equation for segment B and find C sub B is equal to 1.02, and for segment C, C sub B is 1.37. Again, finding C sub B is crucial in order to get this design problem correct. What we want to do next is set up a chart. And this chart will help us keep track of pertinent values that we'll need to use as we go back and forth between tables in order to pick the lightest W shape that will meet the requirement of this beam. So the headings of my chart are going to be segment, MU, or M max, the max moment felt in that segment, C sub B, L sub B, MU over C sub B. And what we do is divide MU by C sub B in order to normalize it so that we can go in and use table 310. Table 310 is designed for cases where CB is 1. However, we can still use it and get in the ballpark for a design problem if we normalize our max moment by CB first. We're going to want to list some trial shapes. We're going to want phi mn when CB is 1. That's from table 310 as I mentioned. And then I like to list phi mp for our shapes too. So these are the headings. of our table. And we're going to make 3 rows. 1 row for each segment. So first we'll have segment A. Looking up in the moment diagram, the max moment anywhere in segment A is 410 kip feet. Again, I'll leave off units to make it easier. We just calculated C sub B as 1.50. The unbraced length was given in the diagram of the original problem, 8 feet. MU over CB is going to be 273.3. And then we'll do the same thing for the other shapes here. Or sorry, the other segment. So the other segment, segment B, for example, 507.7 is the max moment in that. CB 1.02, 10-foot unbraced length. Normalizing that, we get 497.7. Extend my columns here. And we'll do the same thing for segment C. Max moment 472.5 with a C sub B of 1.37. Unbraced length of 6. Normalized moment 344.9. And then now we need to go into table 310 to find some trials. So we're going to enter table 310 with 8 feet and 273.3 to find an appropriate trial section for segment A. This is on page 3-127. So I'm going to continue down, make sure I get my 8-foot reference point. Looks like I need to go to the next page, 3-128. Oh, looks like I need the page before. I need to find 8 feet. Okay, 3-126, we have 8 feet. And I'm going to scroll up until I find a moment of 273.3. And that's going to be right around here. Now once I have that point on table 310, I'm going to go up along the 8-foot length until I hit a solid line. And that first solid line that I hit is going to be a W21 by 44. And when it hits that line and I go across to the left, I find the value of moment to be about 298. So I'm going to go back to my chart here and document that. So a trial is 21 by 44, and I get 298 kip feet. If I were to continue up along the 8-foot unbraced length, the next solid line I would hit is from a 21 by 48. And while I'm here on table 310, I like to get 2 trials per segment in case one turns out to not work. And this 21 by 48, the phi m sub n off of table 310 is 372. Likewise, I can go in and look at the other segments with the with the MU over CB and the unbraced length and pluck off these trial shapes. I get a 21 by 68, 528 phi m sub n, 24 by 68, 588 phi m sub n. And then in segment C, we have 21 by 48 and an 18 by 55. Those phi m sub n's are 394 and 419.